Hi everybody, we are back to do lecture 2 for chapter 6. So last lecture we talked about energy and the types of energy within cells. We talked about thermodynamics and how every living thing needs energy. Well, this short lecture is going to be about the concept of free energy. So that sounds really weird. What does free energy mean, and why isn't all energy free energy? Well, free energy specifically is the amount of energy a molecule has to do cellular work. All right, so free energy was first described by a man named Gibbs. And so the full name for this is Gibbs free energy. And it is symbolized with a capital G. Within cells, we're typically talking about the change in free energy over the course of a reaction. So as reactants are converted into products, how does the free energy of the reactants change as that chemical reaction progresses? And so the difference then between the free energy of the products and the free energy of the reactants is called delta G, which means the change in free energy. And delta G is calculated as the free energy of the products minus the free energy of the reactants. And it's important that it's always in this order, okay? The free energy of the products minus the free energy of the reactants, because the sign on delta G, whether delta G is positive or negative, is going to tell us quite a bit about that reaction. And so if we've got to keep this reaction, or we've got to keep this equation in this order, otherwise our positive and negative isn't going to be consistent, and it's not going to tell us anything. Okay, so we can visualize chemical reactions as equations, but we can also use energy progress curves to explain and understand some things about what's going on in the reaction with respect to free energy. So we're going to do a sample energy progress curve with just a hypothetical reaction. And our reactants are going to be starting up here, okay? So this is the free energy that the reactants start with, and our products are going to wind up down here. Well, reactions don't just go in a straight line, so we're not just going to get this diagonal line from reactants to products, because every chemical reaction has activation energy. And you can think of activation energy as a barrier that you've got to get over before the rest of the reaction can take place. So in this case, we're going to start with our reactants. We're going to have to put some energy in to get over that activation energy barrier, and then the rest of the reaction can proceed. So this energy right here, from where the reactant started up to the top of that hill, is your energy of activation. That's how much energy you have to put in to get the reaction to go. From these energy progress curves, we can also visualize delta G, because delta G is the free energy of the products minus the free energy of the reactants. Well, in this case, our products have a lower free energy than our reactants. And so when you have a smaller number minus a bigger number, the sign is going to be negative. So for this reaction, we would have a negative delta G. We can characterize reactions such as these as exergonic. So you may have learned in chemistry about exothermic reactions. These are similar. It's just they're taking place inside a cell. Okay, so exergonic reactions are reactions that are releasing energy to the cell. Okay, all right. Well, we can also draw energy progress curves for endergonic reactions, where our reactants are starting off lower energy and we've got to move uphill to our products. Remember, our activation energy is how much energy we've got to put in to get the reaction to go. And it is always starts from where the reactants start and go up to the top of the peak. So for an endergonic reaction, we've got a large energy of activation because we've got to go from way down here where the reactant started to way up here on the top of the peak. Okay, so these are endergonic reactions. We're having to put energy, or cells are having to put energy in to the system. Well, if we're going to look at our free energy for this reaction, again, it's the difference between the free energy of the products and the free energy of the reactants. Okay, well now our products have a higher free energy than our reactants, so we're going to have a bigger number minus a smaller number. That's going to give us a positive value. So that reaction would have a positive delta G. So now we're going to talk about exergonic and endergonic reactions, positive and negative delta Gs, in the context of catabolism and anabolism that we introduced in the last lecture. So catabolism, remember, in general, is going from big to little. So breaking big molecules down into smaller pieces. Catabolic reactions tend to be exergonic. They tend to increase entropy. They are spontaneous. Now, what I mean by spontaneous is not that they are fast, okay? A spontaneous reaction doesn't mean that it happens instantaneously. Spontaneous in this context means energetically favorable. So an energetically favorable reaction is one where the cell is getting out more energy than it puts in. Okay, so the change in free energy is more than the activation energy that's required to get it going. Anabolism is essentially the opposite. So we're taking little things like amino acids and we are linking them together to build proteins. Well, that requires a large input of energy. These are also decreasing entropy. So if you think about having thousands of individual amino acids and linking them together to build a protein, the protein form is a much lower entropy because the amino acids all have to be in a certain order, a certain arrangement. The peptide bonds are only between certain atoms. That's much less disorder, so that is decreasing entropy. On the other hand, if you take a big protein and you break all of the peptide bonds and release the amino acids, we are increasing the disorder, increasing the entropy. Anabolic reactions in general, are also non-spontaneous, meaning that they are not energetically favorable, that the amount of energy that has to be put in to get the reactions to go is more than the amount of energy that's released by the reaction. Okay, so we're going to see in the next lecture how delta G and exergonic and endergonic reactions play into the cells actually getting things